Hello, everyone, and welcome to the Nuclear Engineering Summer School. I'd like to welcome you all to the first session of our summer school. This summer school is brought to you by the Consortium for Monitoring Technology and Verification. This is a consortium that is run out of the University of Michigan and includes 14 universities and 13 national laboratories who are working together to develop the new technologies and train students in the areas of nuclear non-proliferation, nuclear safeguards, and peaceful applications of nuclear technology. So as a part of our work, we offer this Nuclear Engineering Summer School. And the summer school is starting today, and it will run for several weeks. The topics that we will cover within the summer school include nuclear science and detection topics, including gamma ray detection, neutron detection, topics in active interrogation, Monte Carlo methods, radiation imaging, fission physics, and special applications, including things like medical imaging. This summer school is a webinar format. There is no cost to participate, and you can find the schedule of our summer school online at the link that you see there on our MTV website. So we have a large number of registrants, 319 people registered for the school this summer. As you can see, this is year 4 of the summer school, and we have a growing attendance. On the graph on the right, you can see the breakdown of the summer school participants. We also have a few students from high school who are participating with us, so that's very exciting. Now I'd like to have a quick poll. So you'll see a poll appear on the screen, and I'd like you to answer the poll as it appears there. The poll is asking, where are you located? Please select where you are located. Okay, I see that the answers are coming in. I'm going to give it just another minute. All right, please finish answering the poll. And here you can see the results. So I see that we have several continents represented here today. Africa, 33 out of 101 attendees. Asia, 25. Europe, 10. And North America, 31. South America, 2 people. And we also have answer to what is your current level? And you can see these answers here. So it's great to have you all here. And again, it's a very diverse group. No one from Antarctica yet, so we're still working on that, but wonderful. Welcome, everyone. So with that, I want to mention that if you attend 80% or more of the lectures this summer, you will be awarded a completion certificate. And you can see here an example of what the certificate might look like on this photo. I hope that you will consider attending 80% or more of our lectures so that you can obtain this certificate. With that, I will hand it on to our first speaker of the series, who is Alexander Kavner. And Alexander is a PhD student in our department. So Alexander, please go ahead and share your screen.
All right, can everyone see?
Yes, we can see.
Okay, perfect. So my name is Alex, as Professor Pozzi just said, and I'm going to be giving the first lecture, and this is going to be more or less an overview of the introductory materials, or an introductory overview as as pertains to the underlying nuclear physics of what's going to be talked about throughout the rest of this lecture series. I tried to keep it at about an upper level undergraduate level. We're not going to be doing any crazy math, but we're just going to talk conceptually about the underlying bases for this work. So obviously, introduction, we're going to talk about the fundamental forces that underlie all of modern physics, including nuclear physics. And then what we're going to do is build up how the nucleus of the atom is built. And then from there, we'll talk about some extra topics just in brief overview, which I know will be discussed in further detail throughout the rest of this summer series. So, as most of you have hopefully seen, the periodic table of the elements is just a one-dimensional linear interpretation of the known constituents of matter. I know it's two-dimensional, but really it's, it zigzags, through like such. And you have light elements that everyone is familiar with, like oxygen, nitrogen, that comprises a large percentage of our atmosphere. And then you get heavier elements and the radioactive elements, which are mostly down here in the lanthonide and actinide series, with a few like francium, radon over here. So, most, if you type into Google or ChatGPT or whatever, show me a picture of the atom, it's to a basic order is going to show you something like this, where you have a compact nucleus in the center and a ring of electrons around it. The size of this thing is incredibly small, and this, entire structure is about sorry, struggling with my pen here. This entire structure in diameter is about 10 to the negative 15. So, or sorry, 10 to the negative 10. I'm sorry, I'm struggling this morning. So this is 10 to the negative 10 meters. And that is 0.1 billionth of a meter. And then the nucleus is an even smaller object, which is about 10 to the negative 15 meters. And so this is what comprises our nucleons, which we're going to talk about. And the electrons orbit around this, though this is a very inaccurate picture, as we're going to discuss. So what are the constituent particles? We have really three building blocks of the atoms. We have the proton, the neutron, and the electron. The electron, as mentioned, sits in a cloud around the atom, or around the nucleus, to form the perimeter of the atom. And we're going to really focus on these two bodies, the proton and the neutron. They have positive electrical charge for the proton and no charge for the neutron. And what you can think about is that's just, you can charge up an object with static electricity, and it's the same thing in that one has a positive polarity, one has no polarity, and one has negative polarity, which is the electron. The mass of these objects is about 940 GeV per c squared. And so for those who know the energy units of physics, GeV is an energy. It is 1 billion electron volts. And an electron volt is just the amount of energy a object with 1 unit of charge, such as the proton or the electron, will have while being accelerated in a 1 volt electric field. And as many of you probably are familiar with the Einstein equation, E is equal to mc squared. We can just divide out the c squared on both sides, and thus get that our mass is equal to this energy term divided by the speed of light squared. The neutron is about the same mass, a slightly heavier, about 960 GeV per c squared. And the electron is the smallest of the three, with a tiny, tiny mass of 0.5 MeV, or I'm sorry, these are not GeV, these are in MeV. So forget this G, and let's just replace it with an M, which is a million. And so then the electron is, so ignore that, and the electron is 0.511 MeV per c. Oops. C squared. So then what we can have in the nucleus is different numbers of protons and neutrons. And what determines an element in the periodic table is not the number of neutrons, but purely the number of protons. So for example, with hydrogen, the lightest element in the periodic table, we actually have 3 possible isotopes. We have H1, which the 1 delineates, so there's 1 nucleon, H2, where we have now a proton and a neutron, and H3, which has a proton and 2 neutrons. And all of these isotopes are hydrogen from the periodic table's perspective, but from a nuclear physics perspective, these are now different atoms or different isotopes with different properties. The most obviously being that the deuterium nucleus is heavier than the proton, as it's a proton plus a neutron, and tritium is heavier than deuterium, as it's a proton and 2 neutrons. And then this gives us other properties as well, in addition to just mass. For example, tritium is now radioactive, which we will discuss further in the slides, as well as upcoming throughout the summer series. So now, if we take our one-dimensional table and instead of just going up in terms of elements, we can now plot, say, 2-dimensional chart where we have the number of neutrons and the number of protons on each axis. And then this gives us, a diagonal chart of the known nuclei. This can be zoomed in the larger plot, where you can see various delineations of both the atomic element, which is written in its letter format, as well as the number of total nucleons. For example, in the pink square, we have antimony 121. So that tells us there's 121 protons and neutrons, and then it is antimony. So from there, if you know the atomic number of antimony, you know that it is 51 protons, which is just, handily here on the zoom in. And then from subtraction, it's 70 neutrons. So that's kind of our brief introductory. And now we're going to talk about why that looks the way it does. So there are 4 fundamental forces in the universe, and don't ask anyone why. That's just the way it is and the way we observe it to be. But you have gravity, which is the force that you are most familiar with. It is what attracts bodies of mass to one another. So that's what holds us to the ground and what keeps the Earth in, say, motion around the sun. You then may also be familiar with the electromagnetic force, which is what powers all our consumer appliances, powers your computer. And this is the delineation of charge, which is the electric and magnetic fields. And depending on how you arrange those charges, you can get different kinds of fields. And then we have the two nuclear forces. We have the weak nuclear force and correspondingly the strong nuclear force. I'm going to start with the strong throughout the majority of this talk. And the strong nuclear force is what builds up the nucleons and the matter to create the periodic table and the chart of nuclides as we know them. And then the weak force, as I mentioned earlier with tritium, is what causes nuclei to decay and what can cause radioactivity, which will be, again, one of the main focuses of this summer school. So the way we know these forces are particles, and don't worry too much about what a particle is, but it's a fundamental unit of force, for example. So what you are most familiar with in your everyday light is the photon, and that is light. And it is not just a unit of light, it is the force carrier of the electromagnetic force. And then, so the most important points on this table are going to be the symbols, but also the ranges. So noted, the electricity and magnetism force has an infinite range. And that's why, you can see the stars from millions of light years away. If you have a telescope, you can see different galaxies, no matter how arbitrarily far they are. Then we have the weak nuclear force and the strong nuclear force. So the weak nuclear force is carried by these W and Z particles. And what is most important here is the range. So this is a 1,000th of a femtometer, which is much smaller than the size of a nucleus. This is the internuclear forces. And then you have the strong force, which is on order about 1 femtometer. So this is about the size of the nucleus itself. And that is, the reason why the nucleus is that size is because that's the range of this particle. As you may remember in the news from a few years ago, the Higgs boson was recently discovered, and there's a hypothesized gravity particle, which would, similar to the photon, have infinite range. But for the point of nuclear physics, we're going to ignore the Higgs and the graviton and really focus on photons and the two nuclear forces. So what I just mentioned is, we have these forces on the right, and they're, the technical term is named bosons, which is named for Siddhartha Bose, who was an Indian physicist, from continental India. And he's the one who developed the mathematics behind these particles. And again, you can see the gluon, which is the strong force, the photon, which is the electromagnetic force, and then again, these W and Z particles, which are the weak nuclear force. And so these are, again, the action terms you could speak of. But there's also the matter. And so the matter is comprised by these other particles called fermions, and that's named for Enrico Fermi, who was one of the most, probably the godfather of nuclear physics, and he invented the nuclear reactor, and also came up with the math which governs the behavior of this left side of all the particles on the left side. And we're just going to pay attention to this, far left column of particles. You have these up quarks, down quarks, and electrons. And then again, the neutrino, but we're going to ignore this for the time being as well. So this is how we build up matter, and this is how we build up nuclear matter. So these up and down quarks are what are going to combine together to give us nucleons. And if you ever go into theoretical physics, you can learn the mathematical formula that governs all of this, but we're not going to talk about that now. So as I mentioned, nuclear matter is built up by quarks, which are the fundamental particle building blocks of the protons and neutrons. And again, what you can think about is these quarks build and these gluons glue. And what these U and D stand for, going back to here, that's the, signifying the up and the down particles. And then the way you can think about the gluons is these are the nuclear forces that keep everything together. So just, an overview of that section. There's two classes of particles. There are the forces, which are the bosons, and the fermions, which are the building blocks of matter. And then nucleons, such as the proton and the neutron, are made up of quarks bound by gluons. And I don't know if we wanted to do questions intermediately or just save those for the end. Just keep going unless one of the moderators speaks up. So, and this is going into a lot of detail of how this all works, but you ultimately have these weird colors. So these are not labeled or not colored with green, red, and blue for arbitrary reasons. These colors signify important things. And while the proton has two ups and a down quark, and the neutron has two down and an up quark, the important thing is that you have these three colors, because in nuclear physics, and this is really complicated, you have a very similar force to positive and negative charges. So you can have, a positive end and a negative end of a magnet, and the positive end will attract the negative end, or the two positive ends will repel each other, or two negative ends will similarly repel each other. In the nuclear physics world, there is three charges, so to speak. So if you imagine that this magnet had, a north, a south, and a west, for example, you can think of that as the North Pole, this is the South Pole, and we will ignore east, but we now have a west direction on our magnet. Except instead of labeling these such as north and south, we label them red, green, and blue, because there are three charges in the nuclear world and three primary colors. And the important thing that allows nuclei to build up is you have to have all three colors built together, or a color and its anti-color, which I'll talk about in a minute. And this is the same way as there's no magnet that just has a north side on it. All magnets have a north side and a south side, and there's no just one-ended magnetic field. So you can think about this in a similar way, that you can't have any just singular pole by itself. Except there's another interesting feature, which is that north and south are opposites. However, red is not the opposite of green, which is not the opposite of blue. They actually have 6, which is now opposite south, opposite west, and opposite north in this example. So you can get a neutral body by either combining red, blue, and green, by combining anti-blue, anti-red, and anti-green, which are denoted here in yellow, cyan, and magenta, or you can draw it with a hat on top. Or the other thing you can do is, again, what I mentioned earlier, is you have green and anti-green, for example. So these are the 5 color combinations that you can get on to build up nuclear matter. And going back, that's why we have these three colors here. So a proton is just, again, two up quarks, as we discussed from the building blocks, with three different colors to make a neutral color, a nuclear neutral color. Now, this has electrical charge of +1, as we talked about, but that's, again, a different concept. That's, the electrical charge as opposed to the nuclear charge. And so then, we can build up these many body systems. And again, you have lots of possibilities, but really the proton and the neutron are really the only two of these that we're going to talk about in great detail throughout the rest of this lecture course. But, you can create all other sorts of possibilities. And the way that nuclear decay occurs will happen, in part through these guys, which we'll discuss in a second. And I know this is, really complicated. A physicist, I.I. Raby, in the late 1950s or early 1960s was quoted as saying, "Who ordered that?" I believe to the discovery of a new kind of meson. But really, what you can think about is we have quarks, which are bound by gluons, and then nuclear matter is built up by three quarks of three different colors. And, these mesons are important if you are learning about the underlying theory in detail, but, just going and building up I repeat this a lot because, again, there's a lot of terms, there's a lot of different particles, but, three quarks with three different colors is what makes protons and neutrons. And, we don't need to worry about this, but a way that, just redrawing the nucleus and how these forces work is you have all these particles jumbled together in not really, we think of them as these spheres, but really it's just the three bodies together and this overarching spherical structure that we see around it, that doesn't actually exist. That's just, a visual representation of this underlying body. Now, it can be, we can treat it as a nice approximation. We can treat these things as single bodies, but in reality, it's, three bodies bound together. And then, so again, going along those lines, we say to first order, the nucleus looks like this, but, if you zoom in, it looks much more like this, where there's not really any hard boundaries between the nucleons within this object. And this, again, goes into kind of the complicatedness of nuclear and particle physics, where we treat them as singular bodies in one view, but in modular bodies in another view. And again, I'm just repeating this for the nth time because when I was learning all of this, repetition is how I made sense of all of it. But our fundamental particle is our quarks, which are held together by gluons, and those build up baryons and mesons, which you can ignore these words and just associate with protons and neutrons. I just want to enter that. So now, I'm assuming we have built up the idea that there is protons and neutrons built up of these fundamental particles, but how do they hold together is this next big concept, and that is the idea of nuclear binding energy. And the reason why we have to ask that is because the protons are positively charged objects, the neutrons are, not charged objects. And so in principle, if you have two positively charged objects, you would expect them to repel each other and to fly apart. And that's where this idea of nuclear binding energy. So through all these gluons and other particles flying around, there's a stronger energy to hold this all together. And what's interesting there is this energy by, Einstein's, equation, E equals mc squared, comes from the mass of the particles themselves. So if, for example, you have a nucleus of mass m, and it has, a total, it has, an atomic number, and or Z is its atomic number, and A is its total number of nucleons. This is less than the mass of the proton, X many protons, X many electrons, and X many neutrons. And this missing mass is what is converted to our binding energy. So our binding energy is the difference between the total weighed nucleus and the sum of all of its parts. And there's this formula that's been developed to calculate the binding energy, and A is these atomic, or is the number of nucleons, which is the number of protons plus neutrons. So that's P plus N. Z is the number of protons, and N is the number of neutrons. And then these terms, these lowercase a's, they are determined by experimental measurement. So that has just been found. We have the masses of all these things, and we've found that these, this linear combination of terms is what creates the binding energy. So what we most talk about commonly is not the binding energy total, but we talk about it in terms of the binding energy per nucleon, or per A. And that's just a different way of putting it. But when you plot out the number of elements and plot out that trend, it makes this curved structure. And what's interesting is you get this peak in iron, and iron, denoted Fe, 56 in particular, is the most stable element, and that means it has the most binding energy, causing it together. And with fission, and probably fusion will be important concepts in the rest of this summer school. But what you generally get is that if you take all the elements above iron, they want to split down, so they will decay until they get iron, and that's releases energy if you split them via fission, which will be discussed in more detail. But the elements lighter than iron want to fuse and combine to reach iron, because this is, again, the most stable nucleus. And this will be talked again more in detail. We're just overviewing that general concept as it is. So now we've talked about the most stable nuclei. So let's talk about unstable nuclei. We have this chart of nucleus, and we get this black trend of very stable nuclei. So the black trend is all the nuclei atoms that we know which do not decay, whereas these pink, blue, and yellow atoms are all the ones that we know of that do decay. So something causes some atoms to be more stable than others, and it's not just binding energy per nucleon. It's not just iron is the only stable element and everything else is radioactive. So we have this question of why are some nuclei more stable than others? And so this goes into the shell approximation of the nucleus. And here we have the atom drawn again, and we see our nucleus in the middle, which for this diagram, it's just depicted as the protons and neutrons. And you have these electrons in rings around it. Now, these rings are not physical rings, but they're rings in energy. So you have this positively charged object here, and then this negatively charged electron, which is held together. And they fill particular energy levels, which is, even though this doesn't physically look like a ring of electrons in energy space, this this looks like discrete lines of energies. And the electrons in the atoms fill up from the lowest energy or the most stable positions to the least stable positions. And inspiration, why we're talking about this is inspiration was taken from the electrons. So when you think about the nucleus, you can view it really as this well of energy, which you can think about this as this, kind of bucket. And you have these two buckets for protons and neutrons. And the protons and neutrons can only end up filling particular energy levels in these buckets. And this model is the derivation basis of the shell model. So again, we fill up these protons and neutrons in these buckets. And what you get, interestingly enough, is just like in atomic physics, you get particular bands that hold particular numbers of protons and neutrons. So the first band holds 2 protons, and so in this bucket you get 2. I only drew 1 because of space, and in this bucket you get 2 neutrons. Then in the next bucket level, or the next layer up in the bucket, you can fit 8 in that level, and then 20 and 28 and 50. And the reason why it's those specific numbers comes down to a lot of math, but what you can take away from this is that there are these, quote unquote magic numbers, which correspond to 2 particles filling a bucket, 8 particles filling, or 8 particles between the 2 buckets, 20 in the next within 3 buckets, and so on and so on. And you can think about, again, this just filling levels up inside the proton and neutron. And again, the protons and the neutrons go into separate buckets in this model. So you have this slow buildup going up energy and energy level. And what we then see is that there's a stable ratio of protons to neutrons. So you have these magic numbers where you have the different buckets filled, but you also want them to be at this approximate ratio. And the ratio changes a bit as you go up the chart of nuclides. It starts off at about 1 to 1. And then it goes to, for the heavier nuclei, it goes to about 1 to 1.5, where this is protons to neutrons. And so what you can think of is if these buckets get lopsided, the atom or the nucleus of the atom then becomes unstable. And what if there are too many protons, for example, this is unstable because these extra protons want to push each other apart as they're positively charged, and there isn't enough there's too much charge and not enough nucleons to provide binding energy. So, you can see that there's now 3 different colors, and focusing on the majority, you have this cyan color, which there is now too many protons. And then this magenta color, where there are too few protons. And the cyan color will decay via electron capture, and the cyan will decay via beta decay. We'll talk about those more in a minute. And that, corrects it closer to this center black line of stability. So the nuclear decays pushes everything towards this more stable line and pushes things more towards these magic numbers. And then if you get really unstable nuclei, they will decay via alpha decay. So really, you can think about three primary decay chains. There's alpha, beta, and electron capture. And we'll now talk about each of those a little bit. So in alpha decay, you have, again, the lowest level of the bucket is filled up by 2 protons and 2 neutrons, because that's the first bucket. The first level in our bucket gets full completely like that. And what turns out to be a very accurate model of this decay is this. You have this nucleus, which is then comprised of this, really stable object of 4, 2 protons and 2 neutrons, 4, and then it gets repelled by the rest of the nuclei. So you have, this smaller body, next to this, larger body, and it's usually attracted by the strong nuclear force, which is this bucket structure again. But every now and then, because these are quantum objects, it can tunnel through this barrier. And if you haven't taken a quantum mechanics course, that's a very tough concept to grasp just conceptually, but particles don't behave normal laws, so it can tunnel outside of this bucket well or potential well and become free. And so this 4-body object stays together, and this, N or Z minus 4 body stays together. And if you have taken quantum mechanics, this is kind of the mathematical or the graphical description of what is mathematically going on, where you have this, allowed space for the alpha particle inside the well, and then a smaller allowed space outside of the well where it can escape. Now it is exponentially suppressed. So the deeper this well, the less likely this escape is to happen. So this is why we only view alpha escape with really unstable nuclei seen, at the ultra heavy elements. So then the far more common decay processes in terms of number of elements which undergo this is beta decay, and then later electron capture decay. And beta decay, again, this is the reason why we have to touch on these underlying fundamental particle physics, is that this is the process by which a neutron is converted into a proton and these other 2 particles. The electron is needed to be there because this is the conservation of electrical charge, where this thing has no electrical charge and this proton has positive electrical charge. So we then need this extra negative. And you also get, again, this mythical neutrino, which we're not going to discuss in the concept of this lecture, but beta decay is what turns a neutron into a proton. And the way that this happens is As I mentioned earlier, a neutron here is 1 up and 2 down quarks. And really what happens is the weak nuclear force, with the W or the Z particle, changes this 1 down quark into an up quark. And that happens inside of the proton or inside of the neutron becoming the proton itself. So this is, just a time graph, but spatially everything is occurring inside of here. And then, it becomes a proton and the electron and the neutrino escape out of it. And then this high energy electron that, just got boosted out of this neutron is then what we can detect to measure if this has occurred or not. And beta, this is just an introductory lecture, so I'm not going too into detail of this, but the detection of these electrons from decaying nuclei is really important in both in terms of the fundamental science, but also again the signature of the presence of these atoms, which is important for safeguards and fundamental the fundamentals of nuclear verification is identifying particles that have come from the nucleus. And then electron capture decay is a similar thing, except here instead of a neutron turning into a proton, you have a proton turning into a neutron, and that is via the up quark turning into a down quark. And this also happens via the W bosons, which is the weak nuclear force carrier. Except here, instead of a electron being ejected, this is a 0 electrical charge. So you have to have +1 electrical charge and -1 electrical charge to add up to that 0. So what you can think of this is the proton is then eating an electron. So the proton will absorb an electron from its cloud around it, and that will allow it to turn into a neutron. And like beta decay, this is another, there are distinct characterizations of this process going on, and the measurement of the radiation, the outgoing particles will be discussed at greater depth in the course. So now transitioning a bit, we're going to be talking about we've already talked about particles being ejected or eaten by this nucleus, but we can also throw particles at the nucleus. So for example, you can throw a neutron at a nucleus. A neutron is able to, if this is our positively charged nucleus with protons and neutrons, and this is our electron cloud around it, the neutron is able to penetrate into this electron cloud and interact with this nucleus in the center. And the most simple interaction is them just bouncing off each other elastically. If you ever play a game of pool or billiards, depending on how you call it, these are just, balls of different mass bouncing around. So you can, throw a pool ball at, say, a bowling ball, and, each of them will scatter depending on how fast you throw that object at it. You can then also have, so we haven't really talked about gammas that much, but a gamma, this is just a photon. And this photon can interact with the electrons because the photon is if you recall from earlier, the photon is this force that acts on electrically charged objects. So it can knock an electron out, just as the neutron can knock around the nucleus, a photon can knock out an electron. However, if you get actually, let me pause for a second. And the interaction here is, so this is just a diagram of the previous cartoon. You have this incoming photon, it knocks out an electron, and what we then measure is an X-ray produced by the relaxation of this empty space. And I know this is if you haven't seen this before in material, this is a complicated topic, but basically you can get additional photons coming out from this electron cloud, from this interaction. And then, they don't just interact via, billiards balls scaling around. A neutron can go in and be absorbed into this higher neutron or into this higher nucleus, which turns it into a new isotope of the same element. However, going back to our bucket model, and I know gamma radiation will be discussed at much greater lengths throughout the remainder of this talk, or not this talk, but the remainder of this school. But the way that you get gamma radiation is this nucleus, or this neutron, when it enters this nucleus, doesn't have to fill, or doesn't necessarily fill, the lowest possible spot in the bucket, but it will drop, after it's joined the nucleus, it will drop down to the lowest level in the bucket, and then the energy associated with this difference, you have some difference of energy because it's gone to a lower energy state, is then released via gamma radiation. And this is another thing that you can do and this will be talked about again in greater depth, is you can identify nuclei based off this released gamma energy, because every nucleus has a slightly different bucket configuration, and then a different bucket configuration when a neutron comes in and enters and then cascades down the states. And so I know that was a lot of material. It's the introductory talk, and my thought about this is to describe the underlying physics that is relevant for the material that you're going to learn throughout the remainder of this summer school in detail. But I wanted there to be lots of time for questions and discussion afterwards.
On the fundamentals of nuclear physics. I'll pass it over to Tessa Maurer, another one of our PhD students at the University of Michigan, for this portion. Tessa.
I think you're muted still.
You're muted.
There you go. Thank you. So thank you so much for that presentation, and we definitely have a few questions here for you from the students. Yep. So the first one is from William, and he asks, I think this was on one of your earlier slides, is yep. 10 to the 10th the approximate diameter of the 1s shell? So yes, this would be, I think, early on in the presentation.
Yeah, going way back. But yes, this 10 to the minus 10 is approximate for for a light element with few electrons in the lowest shell. It becomes larger as you add up electrons and build larger nuclei, but the scaling in terms of electrons is not 1-to-1. So the diameter, if you go up the levels, the next level is not double the size of the first level. It does get larger, but you can get weird geometries. For example, you get this dumbbell kind of shape when you fit additional nuclei in, and then like a ring around, or additional electrons in, and then rings around it. So the atoms do get bigger. This 10 to the 10 or 10 to the minus 10 is the lower bound, but it's not just a 1-to-1. Each electron you add adds 1 unit of size. It's more complicated than that.
Yeah, thank you. And our next question is also from William. He asks, does the forces of these 4 non-infinite range bosons actually stop at their given ranges, or do they approach zero like gravity?
So gravity and electricity and magnetism, the forces don't approach zero because the particle is getting weaker. If you have a light bulb, the light bulb emits X number of photons, and the farther you go away, those photons are all traveling away from they're all traveling away from this object. And so if if you're at this distance, you see, and your eyeball is that wide, for example, you're going to see more of those photons than if you're at a farther distance where they spread out a lot more. And this is actually incredibly important in quantifying radioactive material, because any particle being emitted from a source will spread out like this. Gravity acts much of the same, but these the 2 W bosons, the Z boson and the gluons, they more or less stop at this distance. And the reason why the W and Z bosons, as well as the Higgs boson, stop at that distance is because they have mass, and they will decay into lighter particles. So the reason why the W boson can't reach more than 10 to the minus 3 femtometers is because it doesn't, even if it were going the speed of light, it can't go more than that distance before it decays. The gluons are a bit different. And that goes to the gluons can be color charged, and their range to a femtometer goes to the color charges can't separate themselves that much before the force pulls them back together. So the W and Z bosons just can't make it farther than about the size of a proton or neutron, and the gluons are held back because, again, just like a north magnet attracts a south magnet, the different colors pull everything together.
So we have a few more questions too. So this next one is from Chris. And so his question is, so you can't have more than one of the same color charged quark within a single nucleon? Do they attract or repel similar to negative and positive charges?
So yes. So again, electrical charges is different than nuclear charge, but yes, opposite colors will attract in this manner, and a red and a red will repel each other similarly to how a positive magnet will repel a negative magnet. And that repulsion, the attraction between actually, there's a better slide. Okay, here we go. So this attraction between red and cyan, or red and anti-red, as well as the attraction between different colors, is what keeps these bodies bound together. And then the repulsion of opposite charges or opposite color charges, plays an important role as to why, you don't see, other combinations. There's no other stable combination because any other combination will have a repulsive force in it.
Thank you. The next question is from Rwand. Do the gluons contribute in binding energy?
Yes. So, just as the nucleus is lighter than the mass of the individual protons and neutrons that make it up, the mass of the proton is less than the up plus down. And that extra mass is in the gluons holding everything together. And again, in nuclear physics, you really have to use this Einstein formula a lot because mass and energy are interchangeable in that way. And the masses of objects do not add up linearly because you can transfer mass between energy and energy between mass. And ultimately, that's why nuclear power works. It's just, and the physics can't say why that is. It just describes how it is. I hope that answered the question.
All right, our next question is from Rosalind. When proton converts into a neutron during beta plus decay, doesn't it violate the law of conservation of energy? From where does the proton get its extra energy?
So actually, I think I just skipped it. Yes. So, sorry, could you repeat the question?
Yeah, when a proton converts into a neutron during beta plus decay, I think the question is asking about like the conservation of energy and how that's working in beta plus decay.
Okay, so in beta plus, so electron capture and beta plus decay are very similar. I didn't go into this just because of sake of time, but it's the same, you have the process where it eats an electron, but it can also emit an anti-electron instead of eating. So it can, it's called E plus. And, I just didn't discuss antimatter because of just, time in the course. But yes, the neutron weighs more than the proton, and it actually weighs more than the proton plus the electron. So yes, there is an apparent violation of the conservation of mass and energy. However, that is because the extra energy comes from the binding energy of the nucleus as a whole. So you have all these, you can't think about it as just the proton turning into a neutron. You have all these protons and neutrons together, and they can arrange themselves into a lower energy state. So for example, sorry, I'm bouncing around slides a lot because this is actually a very good question. So if we have this configuration and we eliminate this proton and it turns into a neutron in this bucket here, this entire state has lower energy than before when the proton was here. So that, these two nuclei weigh different amounts, in one where you eliminate the proton and it turns to electron, or it turns to a neutron, and one where it doesn't. So the extra energy comes from the difference of energy from the before and after of this, because it's going to fill that lower bucket. And that's why you really only see electron capture or beta plus decay on this side of the line of stability, because it can only go that way to get the energy for it.
Perfect, thank you. We have another question from Abdul Rashid. Does a neutron have a wave-like behavior when it penetrates matter? In particular, does it have a reflection and transmission components at the same time, like a gamma ray?
Yes. Okay. So that's a complicated question, but okay. So yes, the neutron does have a wave-like property, and what can generally happen between or what generally differentiates how this neutron is going to interact with this nucleus is its wavelength. If the neutron's wavelength is on the order of the size of this nucleus as a whole, it will interact with the nucleus as if it were one body. So that's why you get elastic scattering such as this. If the neutron's wavelength is much shorter, then what tends to happen is the neutron blasts its way through this nucleus, which causes fission to occur. This is not a only or rule. It's quantum mechanical, and so it depends on each atom, and I don't know if they talk about cross sections specifically, but I believe that will be discussed. But we have these in-depth cross-section tables, which are basically what is the relative probability of elastic scattering versus fission, for example, as a function of neutron energy, which is the neutron's wavelength is proportional, its momentum, P is proportional to 1 over lambda, the wavelength, and P is obviously, related to energy. So yes, it does have wave-like behavior, and yes, that wave-like behavior will change which interactions are more or less likely. However, we usually don't discuss that as a function of wavelength. We usually discuss that in terms of neutron energy, but energy and wavelength are, of course, related. And in terms of transmission versus reflective neutrons off the nucleus, that also does happen, though it's talked about in a different way. And what that's usually talked about is in terms of what is this angle. And the scattering angle does not always follow just a flat distribution of if you just threw billiards balls at other billiards balls. This angle can change, and that depends again on the wavelength of the nucleus and the wavelength of the neutron itself. Again, we don't really talk about that in terms of wavelength. We talk about that, or we don't talk about it in terms of wavelength scattering reflection. We talk about it in terms of the neutron energy and the scattering angle, but the underlying physics of why some angles are more likely than others is again going down to this reflection versus transmission coefficients.
Perfect. Our next question is from Eric. Is it just a coincidence that the most stable nucleus happens to be magnetic?
I don't believe so. I could be mistaken here, but yes and no, depending on how you mean coincidence. So just as we have this Oh, here we go. Just as we happen to have this, or we have this shell-like structure that is very similar between the protons and neutrons filling the nucleus. You have the same structure of electrons filling in around the nucleus, and magnetism goes towards the spin and the filling of these shells. So the nuclear spin and the electric spins are related in the sense of, protons and electrons go 1 to 1. And so, these delineations here correspond with, angular momentum and spin states. However, beyond that, I don't believe there's any known correlation as to why it's more nuclear stable and has magnetic properties. That's just how the spins align. And then the reason why the spins align for that nucleus in a way that produces magnetism is related to a similar principle as shell filling. But other than that, I don't believe they're related.
All right, we have another question from James. You mentioned the atomic nuclei are like magnetic poles. In that context, if we were to imagine it split, for example, red and anti-red, which would each then become a new dipole?
So that was a very, very, very long debated question in physics. The question of could you get a monopole, or split away these quarks, and many years of experimental physics went into determining this question. But the way you can think about it is, let's say you have a red here and anti-red here, and they're bound together by these gluons. The more you pull these apart, just like the more force you get, the more you charge up an object, the stronger the attractive force back in together goes. And eventually what happens is you take so much energy to pull these guys apart that you'll get a new particle forming at each of them, and it'll split into two particles. So what, just like it takes energy to separate two magnets, it takes energy to separate two colors, and the gluons are different. There's no real classical analogy to this, but the further you separate these guys, the stronger the recombination force wants to be. And eventually, if you are able to split them far enough, they will, just turn into it'll go from one particle system to two particle system. And that's why, even though that's why the gluon has this range. If you try to separate particles, color charged particles more than a femtometer, you will just get more particles created from that energy. Hello? I think Tessa just dropped out there.
Yes, Alex, it looks like we might have lost Tessa. So if you want to continue, be able to see the Q&A.
Yeah, well, I very much, these are very good questions, and I'm happy you're asking them. In the sense that, it shows that I didn't just spout nonsense for an hour. Okay, so Ali Dawood asks, orientation of quarks and their numbers in the core of neutrons and protons was observed. Yes. So a lot of these, a lot of this fundamental particle physics was figured out at Fermilab in Illinois, and a lot of those structures and observations were basically discovered in the late 60s to the mid 80s at various experiments at Fermilab in the colliders that they have built there. And if you want, the history of those experiments is very long and rich. But yes, these things were all observed, over the decades of experimental physics. And I see Tessa's back. Okay, maybe still frozen. Okay, so the next question is from James, and it says, you mentioned the atomic nuclei are like magnetic poles in context. Oh, we just did this one. Okay, so the next question is, why does the Higgs boson particle have electroweak force? Okay, the Higgs particle is a very, I'm going to just try to do this briefly. The Higgs particle gets its existence from the idea that at a higher energy level, these guys, the photon and the W and Z bosons, come from the same place, or the same underlying fundamental force. However, we see a difference, mainly in the masses. And when you look at underlying group theory and a lot of mathematics, it comes out that one particle will have no mass and three particles will have mass, and the Higgs boson is created as the splitting of that symmetry. This is a really complicated physics that you really don't get into until like your second year of quantum, or second semester of quantum field theory. But basically the Higgs boson comes from the separating of the photon from the W and Z bosons of their from one underlying fundamental field. And there are other theories of physics where all of the particles come from a single underlying field. However, there is no experiment other than the Higgs particle, which only interacts with electroweak. There's no experimental evidence for that yet.
All right, I think I'm back now. I'm so sorry. My Wi-Fi dropped. And so did you just answer Brock's question?
I answered Safis Sakib. I'm sorry if I'm so the next one is from William Redding. Yes, so I was mistaken earlier. I was getting ahead of myself in the presenter notes, but yes, the proton and neutron are 950 some MeV, but yes, the W and Z bosons and Higgs bosons are GeV, and that goes into why their range is so short, is because they're so massive they will decay away very quickly, and that's why you need very high energy particle colliders, such as the Large Hadron Collider in France, to see these particles get created. You don't need the Large Hadron Collider, I believe, when it discovered the Higgs boson, went up to 2 to 4 TeV, or about 2000 GeV in energy. You obviously don't need that. You only need 126 to create a Higgs particle, but you know, not all the energy goes into the Higgs particle, so you need higher energy, you know, and then count out what it all goes into. So the neutron to proton ratio of hydrogen, you know, so where was it? So protonium and deuterium are stable. The proton, as far as we are aware, does not decay. There are theories in which the proton is unstable. However, there has never been any experimental evidence. So people have looked for the unstable decay of a single proton, hydrogen, and deuterium. However, it has never been observed experimentally. So as far as we know, the proton is stable, and the proton plus the neutron is a stable body. Tritium, however, this becomes unstable and will decay. You know, the reason why the proton doesn't decay, you know, that then goes into higher unsolved physics. You know, we just have experimental evidence that this thing is stable and does not decay. And, you know, not all physics is not finished. Why the proton is stable is, you know, still a question in modern physics. Okay, what actually determines whether a nucleus undergoes beta decay or electron capture? Okay, so this goes into a question I answered earlier. So these cyan, you know, at the just drew that wrong. So these, you know, cyan nuclei undergo electron capture or beta plus. Again, you know, only so many things I can say in an hour. And the reason why these guys undergo electron capture decay and not beta decay is because they have too many protons. So these ones, you know, the positive repulsion power of 2 protons in the nucleus is too great. And rather than that fissioning the nucleus or causing it to fission, you get, you know, one of these protons turns into a neutron via the capture of an electron. And then, you know, where we talked about earlier, the reason why it likes to do that is if you have, you know, these buckets of nuclei and you have, you know, that P and this N, you know, this proton going to a lower state of neutron or a lower bucket of neutron number pushes things, you know, closer to this black line and is more stable. And the reason why it's more stable is because the neutron, you know, there's too many protons. So now it turns to a neutron to get rid of that extra electric charge and go into a more stable bucket configuration. Beta decay happens for the opposite reason. You don't have enough protons in the nucleus, and not having enough, you know, you'd think, okay, well, protons are positive and repel, but there shouldn't be a problem with being not enough protons. You know, you can add nuclear, you know, tons of neutral bodies. And the reason why too many neutrons is unstable is because the neutron itself decays. So if you have too many neutrons, then one of the neutrons will go into a proton plus, you know, an electron plus a neutrino. And neutrons by themselves, if you just have, a neutron sitting in a box, the neutron itself will decay. And so the reason why beta decay occurs is because the proton is more stable than the neutron. So the neutron wants to go to the proton. And so if you have too many neutrons, then that happens.
All right, I think we have time for one more question.
Yes. Okay, so I'm gonna get. Okay, I'm gonna try and answer the last questions all real quick. So going in reverse order, the electrons can enter the nuclei, and that's how electron capture occurs. So for this, proton to go to a neutron, you need to have that electron, and that, due to quantum mechanics, happens every now and then. Yes, neutrons are unstable in isolation, and the reason why they are stable in nuclei is because you constantly have this process of neutrons and protons turning into one another. They're constantly exchanging up and down quarks via, these two quark systems. And so the neutron is constantly switching between these are quantum mechanical objects, so they never just quite exist by themselves. But if a nucleus has too many neutrons, then it can't do this. And then the last two I'm going to answer together is spin. So I mentioned spin here. Spin is just a fundamental property that particles have, and that determines how they fill the boxes. So the reason why there are, it's not just 2, it's 2, 8, 20, 50, is because the buckets aren't just aligned in, one energy space. It's a 3-dimensional object, and the spin is its kind of orientation in space. Gravity is a spin 2 object, because actually, I'm not sure the underlying theoretical reason, but we know it experimentally has to be because the gravitational wave detectors detect more than just one polarization scheme. So I don't, this is probably going way over, and the underlying physics, that's beyond my theoretical physics knowledge, but we observed gravitational waves, and unlike light, which can have 2 polarizations, gravitational waves have either 4 or 8 polarizations possible. And that's because, and that can only happen if it's a higher spin system. Why it's a higher spin system, that goes into theories of quantum gravity, which we do not have a successful theory of quantum gravity. So I'm not sure if a theorist can probably answer this question and give a better answer to that, but very complicated theoretical physics. Experimentally, I know that's what we've observed.
Yeah, and right before we wrap it up, I know we didn't have a chance to get to everyone's questions, so if you wouldn't mind, I know you shared briefly your contact information,
yes,
but that might be helpful to show again, just in case anybody has questions that they didn't get a chance to get answered here today.
So these are my 2 emails. I guess use A. Kavner unless, yeah, just use the first email, and please put, MTV Summer School or something like that in the byline or in the subject, just, for I'll get to it faster if you put something related to MTV in the subject.
Yeah, well, thank you so much for your presentation. That was great. And thank you for answering all the questions we had. Yeah, so.
Yeah, no, those were all very, very good questions.
Yeah, thank you to the participants.